Okay, so one of the problems is to find the pH. So we're given a problem of 0.25 molar HCN. And they asked us to find the pH. This is all they've given us for this problem. You might say to yourself, I don't even know where to start here. Well, there is a list of known Kas for acids, and we can look up hydrocyanic acid and find that it is 6.2 times 10 to the minus 10. Now, I do want to tell you that the acid dissociation constant, just as you would expect with all we've learned about equilibrium so far, is temperature dependent. So if you look it up and you find a different answer, that's the reason why. So my Ka value, 6.2 times 10 to the minus 10. So here's what we're dealing with. This is a weak acid, very weak. You can see how small my Ka value is. So when it's in solution, it's going to produce very little H plus and cyanide ions. So let's do an ice chart and figure out what's going on here. Before any dissociation occurs is what the I means in an ice chart for an acid. Remember, ice charts we put molarities into. BCA charts we put moles into. So you do not have to do an ice chart every single time, because remember I told you each of these ice charts is going to have the same format. So if you do 10 of them, they'll all have exactly the same structure to them, because each of the acid problems is only talking about one piece of acid, one H plus falling off, regardless of how many H pluses it has. So remind ourselves that our general form of our acid problems is always going to be x squared over the initial concentration. Because you'll see if we do Ka is the concentration of the products over the concentration of the reactants, it's always going to be X times X over initial concentration minus X. And for our purposes, we're always going to ignore that X, especially for this one. The Ka is so small that we know we would not need to include that. So it's going to be X squared over 0.25 every single time. And that's going to equal 6.2 times 10 to the minus 10. I just looked this up too, so I don't even know if that's the Ka that I had used for the answer key. Just an FYI. So you get a value for X of 1.24 times 10 to the minus 5. Remember, X is H plus. So the pH, the general form for the pH would be the negative log of X in these problems. These are formulas you can count on for all your acids. So negative log of X gives me a pH of 4.90. So those are the types of problems that hopefully we're getting a little bit more comfortable with. And I'm going to show you now what a different type of problem might look like. So this is a couple ones down, and it says that I have a weak acid. Here's the general form for a weak acid, is HA. With a concentration of 0.20 molar and an H plus concentration of 9.86 times 10 to the minus 5. And they're asking us to find the Ka. So this right here is our initial concentration. This right here is X. So I'm going to skip over the ice chart this time so you guys can see what that looks like. Because remember, Ka is X squared over initial concentration. So Ka is going to be 9.86 times 10 to the minus 5 squared over 0.20. For a Ka value of 4.86 times 10 to the minus 8. They also asked us to find the pH. Even without an ice chart, I can do that because remember, pH is negative log of X, or negative log of 9.86 times 10 to the minus 5. And I'll get a pH of 4.01. They also asked us to find a new one, which is called percent dissociation. This is going to look a little familiar to you because the percent dissociation is exactly the same calculation as the 5% rule. The percent dissociation is the part that falls apart into H plus and OH minus. So the part that dissociates, not OH minus, A minus. Over the initial concentration or the whole acid. So HA had a concentration of 0.20, and they told us that 9.86 times 10 to the minus 5th is the concentration that will fall apart. So it will be 9.86 times 10 to the minus 5 over 0.2, and to turn it into a percent, we multiply by 100. And we get an answer of 0.0493% dissociated. So that's the percent of molecules that are no longer HA anymore, but instead are H plus and A minus. The smaller the Ka, the lower percentage of molecules dissociate. Does anybody have any questions?